Ladies and gentlemen, welcome everyone to our first talk here today in the bar room regarding bridging the gap between traditional machine learning using scikit-learn and the rapidly evolving world of AI with Hugging Face and Skorch. I'm Johan Reinhardt today, and I'm here to introduce our first talker, Benjamin Bossan. Benjamin is a machine learning developer at Hugging Face and a maintainer of the package Skorch. Let's welcome him with a warm round of applause. I hope you enjoyed today's talk, and please keep your questions for the last 5 minutes. Benjamin, the floor is yours.
Yeah, thank you a lot for the introduction, and yeah, so many people here. I'm very grateful. So if you think this is yours, this talk, you're wrong. It's up there, but I guess now you're stuck with me. So yeah, today I'm going to talk about how you can extend your scikit-learn workflow with Hugging Face and Skorch. And yeah, it's gonna be tough to bring this in 25 minutes, but I'll do my best. And then we have 5 minutes of questions at the end, hopefully. So if you're in this room, I assume that you all know scikit-learn. It's the bedrock of machine learning in Python, and it really has almost everything, I'd say, that you need. So lots of models, cross-validation, metrics, visualizations. So really, if you're using anything related to machine learning, you should be using scikit-learn. But it's missing a little bit on the side of deep learning and neural nets. And if that's something that you're interested in using with your scikit-learn workflow, then you're on the right talk. And to get to our goal, we need a few ingredients. So the first one is Skorch. So I'm one of the maintainers of Skorch. We have another one sitting there. And it's a quite old package by today's standards in machine learning. So it was released like half a year after PyTorch was released. And we built it because we were scratching our own itch because we wanted to use PyTorch, but with the scikit-learn API, and this is what Skorch provides. It's really built on PyTorch, so it doesn't have multiple backends like TensorFlow, but it's yeah, still very versatile, so you can check out the examples and the docs if you're interested in learning more. And here on this slide, I have a little bit of a diagram of how Skorch integrates with the bigger ecosystem. So I know it's quite a lot. You don't have to learn it. It's not going to be on the test. But to get a broad overview, like on the outside, we have scikit-learn, and that works with the Skorch classes like neural net classifier or neural net regressor. So you can just drop it in if you have a KNN classifier or a linear regressor. You can just swap it out, basically. It should work. And then we have different components inside of Skorch, which connect to the bigger ecosystem like Hugging Face, PyTorch, and other libraries outside. And yeah, today we are gonna focus on the Hugging Face side. So what is Hugging Face? Oh, sorry, a little bit of code first. So this is how it looks like when you try to use Skorch without Hugging Face first. So here we import a neural net classifier. So let's assume we have a classification task. And then we define our module. So if you have worked a little bit with PyTorch, you already know how that works. You subclass the nn.module, then you write your code, and you can just use basically any code here that works with PyTorch. So Skorch doesn't make a lot of assumptions. And then you pass it into the neural net classifier here. So can you see the cursor? Yeah. And then you can pass the module, a couple of hyperparameters, so like the number of epochs and the learning rate. And at the end, you can also modify the training a little bit with callbacks. So here we are using epoch scoring, which just means that at the end of the epoch, we calculate a score. And for example, if you look at this argument, scoring equals rock AUC, you will probably be familiar with that because the same argument in scikit-learn. When you do scoring scikit-learn, you can also pass like a scoring argument like this. And the reason is that we are using scikit-learn under the hood. So the metric is calculated exactly as you would expect. And then at the end, of course, we can just call net.fit, net.predict, net.predictproba, so like you would with your normal scikit-learn classifier. And predict and predict proba will also return numpy arrays, so exactly as you would expect from scikit-learn. Okay, now we get to a Hugging Face. So probably most of you have at least heard of it, maybe used some parts of it, but I don't think that there's anyone in the world who has used everything from Hugging Face because it's really gotten quite big. And yeah, we will look at some parts of it today, but I really couldn't cover all of it. So there's going to be a few slides in the backups. So if you're really interested in learning more, then you can later check out the slides and look at what more Hugging Face has to offer. So today we're going to focus on those parts, so transformers and tokenizers, which is probably the biggest one. We will look at parameter-efficient fine-tuning, which is something that has emerged in the last few months as something really important with big models. We will look at accelerate, which will help us train our models faster. And then we will have a section on large language models. And by the way, the slides are all online. I'll post the link later, so you don't have to take any notes or photos. Okay, so transformers and tokenizers, what's that? So transformers is probably the most well-known Hugging Face package. And it implements a lot of transformers-based pre-trained models, so something like BERT, GPT, Falcon, Llama, and so on. And if there's something new coming out this week, probably next week it's going to be in transformers. So you really have a very big choice of open source models. And it also implements non-transformer stuff, so it's not really just transformers anymore, but this is what people are using it for mainly. And then there's also the Hugging Face tokenizers package, which if you're working with text, you have to tokenize it first, and this is what tokenizers is for. So it really implements a lot of different techniques, byte pair encoding, word piece, sentence piece, and so on, but also like the padding, truncation, so everything that you need to tokenize your text. And now let's take a look at how we can implement it in our scikit-learn workflow. So first of all, we import the auto model for sequence classification because we assume here that we want to do a text classification task. And then we will write our PyTorch module, as I mentioned earlier, and this is a very light wrapper around the auto model. So let's look at what we need. We have an init, which takes two arguments, the name, which is going to be the name of the model, and the num labels, and this is going to be the number of classes. So scikit-learn calls it classes, here it's labels. And we will just load the pre-trained model here and pass the arguments. So nothing really happening there. And for the forward, we would just call the model and return the logits. So it's a really light wrapper around Hugging Face transformers. And then as a next piece, as I mentioned, we need the tokenizer. So from Skorch, we can import the Hugging Face pre-trained tokenizer. And this works as a scikit-learn transformer. So you can call fit and transform on it. And most notably, we can put it inside a scikit-learn pipeline. So this is just a normal scikit-learn pipeline, with the first step being the tokenization. Second step is our neural net classifier, which takes the module that we just defined. And something to be aware of, if you remember, we had those two arguments, name and num labels. So how do we get this to our module? Well, we use the argument module double underscore name and module double underscore num labels. And if you know a little bit of scikit-learn, you know this double underscore notation, which just means like forward this argument to this part. So here we are forwarding the name to the module. So that's how the module knows its arguments. And also something to be aware of, here we are using the model distill BERT base uncased, which is like a smaller BERT model. And the model name is going to be the same here for the tokenizer and for the PyTorch module itself, so that the two fit together, because if they don't, then you will get incorrect results. And the rest should be pretty straightforward if you know a little bit of scikit-learn. So you can just call fit on the pipeline. We pass our data, so that would be text here. And in the Y, we have our labels. And then Skorch will internally do a train validation split of your data. Of course, you can disable that. And then during a training at the end of each epoch, we will see a little bit of progress. So you can see the train and validation loss. You can see the accuracy on the validation data set and the time that it took to calculate all of that. And then once we are finished with the training, we can just call predict and calculate the accuracy using scikit-learn. So yeah, that's basically in a very short time how you can use transformers and tokenizers in your scikit-learn workflow. And of course, if you're using scikit-learn, you might also want to do something like grid search, and that's also possible. So if we go going back 2 slides, we can see that in our pipeline, the second step was called net. So we can use this name to address the parameters that we want to grid search on. So for example, here, for the net, danda module, danda name, we can pass different modules, like we can try distillbird, but we can also use another bird model. And of course, we can also change the other hyperparameters, like the optimizer, the learning rate, and the number of epochs. And then we just put it all into a scikit-learn grid search, and it will try out all the different parameter values. So at the end, you know which ones are best for your use case. And here in the slides, I have a bunch of links. If you want to know more, if you want to see complete examples and notebooks and run it for yourself, you can just look at those slides later. And for example, there's also a notebook for vision transformer models, so it's not only for text, you can also use it for other modalities. So really recommend it to take a look. Then next in line, I want to talk a little bit about parameter-efficient fine-tuning. So what's that? So there's this library called PEFT from Hugging Face, and it implements a couple of techniques that help you work with really large models. So we are talking of billions of parameters. And if you want to fine-tune the model, so like we did previously with the BERT model, but it's really large, that can be a problem. So it will take a lot of memory. It will be very fickle. So maybe you want to have a better technique, and that is where PEFT comes in. So some of the techniques in PEFT are like specialized for language models. So we are not going to look at those today, but there are other techniques like LoRa, which is short for low-rank adaptations, which work with basically any kind of model. So we're going to see how we can use that. So for this problem, let's just imagine we have a very simple model, a multi-layer perceptron with a hidden input layer, hidden layer, output layer. And we want to apply parameter-efficient fine-tuning on this model. How can we do that? So we will import PEFT, and since we want to use LoRa, we will first create a LoRa config, which is like the specification of how we want to use it. And there we have a couple of arguments. So R is the rank, which basically tells you like how compressed those extra parameters are going to be. We will also say which layers of our MLP we want to target. So 0 was the input layer, and then 2 was the hidden layer. And then we also define the modules to save. So those layers are like trained normally without any adapters applied on top. So that's often recommended for the classification head if you're on a classification task. And once you have the config, we just pass it to the PEFT model function with the MLP. And what we get at the end is, yet again, a PyTorch module. So we can put it into the neural net classifier and fit it, and it will just work. And by the way, in this case, we will only train 1.4% of all the parameters of the model. So the rest is frozen. And this is why it's efficient, because we don't have to calculate the gradients on all of those parameters. We only train a small part of the whole model. And if you're working with large language models, it's like if you don't have a giant cluster, it's almost a necessity to use some of those techniques. Also interesting, maybe if you want to just save those 1.4% of the parameters that were trained and not the whole thing, which can be quite large, you can also do it by calling the save pre-trained method. And then you can see that this adapter, that's how it's called, is like only 1% of the size of the full model. So it also makes it much easier for you to share your fine-tuned model with others. And as always, a couple of links if you want to learn a little bit more, especially quantization is also getting very important recently, so that's also supported. Next, let's look at Hugging Face Accelerate. So this is a library which makes training faster, also can be used for inference, but mostly for training. And there are a couple of ways that you can achieve it. So one is very straightforward, is parallelism. So if you want to use, for example, distributed data parallel from PyTorch, it's going to be much easier if you use it with Accelerate. But there are also other techniques implemented there. And here, for this example, we want to look at something which is called mixed precision training. So usually all your weights and data is in float 32. But that's not always necessary, so we can go down to lower precision and get very similar results, but be much faster. So let's check out how we can do that. So first of all, we need something from Skorch, which is the accelerate mixin. So it's just a mixin class that you can combine with any neural net class from Skorch. And then it will basically add the capabilities to use accelerate on top. And then we use the accelerator class from accelerate and instantiate it with the argument mixed precision equals fp16. So that means we want to use floating point 16 precision for our model. And then the rest is just as you always do. So just initialize the net, pass your custom module, and when you call fit under the hood, everything will be taken care of so that you're using fp16. So that will mean that it's going to be much faster to train your model and take less memory. And there's much more that you can do there, but this was just one example. And as always, check out the links if you're interested in more. And finally, something that I want to talk about is something that we added recently to Skorch, which is support for large language models as zero or few-shot classifiers. So what's the deal with that? You probably all heard about the back then GPT-3 release, that you can use these kinds of large language models as few-shot learners or zero-shot learners. And something specific would be for classification. So you can put in a text, maybe it's going to be a review of a product and you want to know whether it's positive or negative. Then probably you don't need to train a model at all to determine that, because a large language model can answer that question for you. And if you want to do this kind of work in a more systematic way, I recommend to take a look at the zero-shot classifier and few-shot classifier that we have in Skorch. And those use Hugging Face transformers under the hood. And I will show you how it looks like. So here we have a zero-shot classifier. So let's assume we have some data, and we want to instantiate the classifier using the Hugging Face model big science blooms. So we just pass the name of the model, and then something interesting happens. So during the fit call, we don't pass any data because we don't need it. It's zero-shot. We don't need any data here. The only thing that we need to pass is the labels. So for example, for the sentiment analysis would be negative and positive, so that the model knows which labels it should predict. And then during the fit call, no fitting happens. It just loads the model. That's it. And of course, you can use predict to get the labels back that the model predicts for your data. And also interestingly, you can use predict proba, so you will also get back the probabilities of the model. And that's maybe a bit surprising if you worked with large language models, because usually you just get the generated tokens, but we found a way also to get you the probabilities of those tokens. And of course, you can customize it. So for example, if you think the default prompt that we are using doesn't fit your task very well, you can define your own prompt. So here we have just one big string. It has two placeholders, the labels and the text. So labels would be positive and negative, and then the text would be the review that you want to classify. And then we just use the prompt here with the same model, and then we can predict the labels based on that prompt. And of course, we can also do a grid search. So let's assume you have a couple of prompts that you want to test, maybe a couple of different models, so like Bloom's, GPT-2, or Falcon. You can do a grid search on top of that. We can define a couple of metrics that we're interested in, and then just pass it to grid search CV from scikit-learn, and it will do a systematic study of which language model, which prompt works best for your task. And then there's also few-shot learning. So that means that we take a couple of examples and demonstrate to the language model what it should predict for those examples. So here in this case, we do have to have some training data. So we have to split it first. And then we pass the training data during the fit call. But the training data can be quite small. So here in this example, we only have 5 samples. So we will take 5 examples from the training data and augment the prompt with those examples. And then basically the rest is the same as with the zero-shot classifier. And then at the end, we can again call predict and calculate the accuracy of the few-shot classifier. So maybe you're asking yourself why you should be using that. So first of all, again, it's a scikit-learn classifier, so you can just swap it out, see if it works for you or if it doesn't. And one nice thing is that it forces the model to output the labels that you gave it to the model. So as you know, LLMs can steer off on the wrong path and predict something very unexpected sometimes. So there's no danger of this happening here. And as I already mentioned, you get probabilities, which is also not something that you usually get. We have also implemented some caching for decoder-only architectures to make it a bit faster. And of course, since it's using Hugging Face transformers, you have access to all of those models. So you have a wide choice for your use case. And that's especially important if you have maybe some data that's sensitive or so, and you don't want to send it out to OpenAI API or anything like that. It will all work locally. So if you have only very few labeled samples, or if you're bootstrapping your task, then maybe you can think about using the zero-shot classifier or few-shot classifier. Also, if you already know you want to use an LLM, just want to study it systematically, it will also be a good fit. And we also added a few things that help you debugging bad outputs. And for some domains, LLMs are also very good, especially if it requires very deep understanding of the sentences. On the other hand, if you want to have something that's very fast, you should not use LLMs. They are just too slow for that. Also, if you have a bunch of labeled data, probably just use a normal scikit-learn model that's supervised. It will work better. And if the task is really simple, maybe something like bag of words will just be more efficient for you. OK, then some links. And let's wrap this up. So today we learned how we can use Skorch to help bridge the gap between scikit-learn and the Hugging Face ecosystem. There's a lot more that I wanted to talk about, but I didn't have time. So check out the backup slides of this talk. So like vision models, you can customize your tokenizers in grid search, the best hyperparameters for them. You can use the Hugging Face Hub to store checkpoints. You can use safe tensors, which are like a persistence format that is safer than Pickle. So there's a bunch of stuff added. And of course, you can also combine all of those techniques. So you can have a scikit-learn pipeline in a grid search with tokenizers and transformers, made faster with accelerate and more efficient with path. So all of that works together. So here are some links, especially the last one for the slides. And yeah, thanks everyone for listening. And yeah, I take questions.